Welcome back everyone. So in this lecture we will talk about determinants, cofactors and adjoints of a given matrix. Okay. So you're given a matrix, we'll learn how to calculate the determinant of a matrix. So determinant is a very important information about the matrix. Okay. It actually calculates the volume of a given linear transform over here, but we won't be going into those details because there are too much of maths over there, right? But we'll be only focusing on the discrete terms, the part which is required for this discrete maths course. Okay, so that is just finding the determinant and assigning a number to a matrix. Okay, so after that we will study about cofactors and then adjoints of a matrix, and we'll use all this information, that is determinants, cofactors and adjoints, to find the inverse of a matrix. So we have already seen one method to find the inverse, but now we'll see one more method. Okay, so let us start now. So yeah, so let us start with determinants of a matrix. Okay, so definition: determinant of a matrix is a function that assigns each n cross n matrix to a scalar. Okay, to a scalar. So basically a matrix is, you can think of it as a vector or collection of vectors, right? And you're assigning it to a scalar. Okay, so let us see the formula for calculating all this. I'm not going too much into the maths of this. I'm just directly going to give you a formula and we are going to calculate the value of the determinant. How this formula comes, there's kind of a lot of theory involved in it. Okay, that is something which we don't even teach our pure math students. It's only taught to some senior MSc level math students. Okay, so formula, first we'll study the 2 by 2 matrix. Okay, 2 by 2 matrix case. So let A be equal to a 2 by 2 matrix which is given by A, B, C, D. Okay, then determinant of A is given by A into D minus B into C. Okay, so in other words it's AD minus BC. Okay, so just to give you an understanding of what I have done here, is I have multiplied this element with this and then this element, and I have subtracted this. Okay, so first you multiply the diagonal element and then you subtract the anti-diagonal element. Okay, so that's about the 2 by 2 case. Yeah, I should have mentioned that for 1 by 1 matrices also the determinant is there. Okay, sorry, 1 cross 1 case, we won't be using this much, but it's better I mention it. Let A be equal to a single 1 cross 1 matrix A, then determinant of A, I should have written determinant or not just D of A, just change this here. Okay, determinant of A is just going to be a single A. Okay, just a A without the boxes. When you write this square brackets around, it means you are talking of a matrix. If you just write it like this, you are talking of a scalar. Okay, yeah. By the way, I had written D over there, no? So I changed it to DET. Yeah. Now also just those notations we uses, this notation, because writing this word DET also will be a problem after some time. So notation, we denote the determinant of A by determinant of A. Okay, you can write capital D also, huh? No harm. Okay, sorry. Yeah, by capital A also you can write, capital D also you can write, determinant of A. Or one of the most commonly used notations is this, you put two bars around it. Okay, so also called as the modulus notation. So or this, right? Okay, yeah, so let us do some examples now. Okay, do a couple of examples, then we'll go to the next case. Okay, find the determinants, find the deter find the determinants of the below matrices. Okay, find the determinants of the below matrices. Find the determinants of the below matrices. So we write down 1. A is given as, tell me some numbers. You tell. Yeah, what numbers you want? 23, 24, 9, 10. Okay, so these are the numbers you have given. So this becomes, yeah, so determinant of E will become what? 23 into 10 minus 24 into 9. Okay, one is 230, second one will be 24 into 9, so 240 minus 24, right? So that is 216. Okay, so this will leave you with a number as 14 over here. Okay, so determinant of A is equal to 14. Okay, so moving on, we won't be solving problems in the one by one case on that, it's too trivial. Okay, so next two, yeah, give the matrix first. Yes, you tell some numbers now. Which numbers you want? 2, 3, 6, 9. Okay, so this is the matrix given to you. So let us calculate this. So determinant of A over here is equal to yeah, so this will become 2 into 9 minus 6 into 3. This will leave me with 18 minus 18 is equal to 0. Okay, so the determinant of this matrix is equal to 0. Okay, one more example will do. 3 A is equal to 2 3 4 0. Okay, so this will leave me with determinant of A okay. Determinant of A is equal to 2 into 3 minus 4 into 0. Okay, so this will leave me with 6 minus 0, which is 6. Okay. Okay, so yeah, so this is done. Yeah, before we go ahead now since we have done sufficient couple of examples, let me define some more things. Okay, definition. We say that a matrix A is singular if and only if determinant of A is 0. Okay, if and only if determinant of A is okay. Singular matrix means a matrix whose determinant is 0. Okay, now some properties which follow. Okay, this is the definition of a singular matrix. uh, so there are some properties here. I won't be proving those properties, but I'll just state them. Property okay, if the rank of a n cross n matrix is less than is less I already wrote the word now, so I need to write the notation. Yeah, so is less than n, then determinant of n cross n matrix A, will call it, then determinant of A is equal to 0. Okay, okay. So if you have a matrix of rank of size n cross n whose rank is less than n, then determinant of A is 0. Also the converse is true. Also, if determinant of A is equal to 0, then if determinant of A is 0, then rank of A is equal to rank of A is strictly less than n. Okay, it's not equal to n. Okay, so it's an if and only if result actually. If rank is less than n, then determinant is 0. So if determinant is 0, then rank should be less than n. Okay, one example we have on top over there. See this example which is there on top with the matrix which has determinant 0 here. Observe that the second row over here is just 2 times the 3 times the first row. Okay, so if what you can do, then you can perform the operations. If you try to find the rank of this matrix by row reduction, right, you can perform the operation R2 1 minus 3 and you will be left with this matrix here 2 3 0 0. Okay, then you divide by 2. After you divide by 2, you will be getting 1 3 by 2 0 0. Okay, 1 0 3 by 2 0 0. So the rank of this matrix is 1. Okay, which is less than the number of rows in this matrix. Okay, in this case n was equal to 2 and rank is equal to 1. So rank is 1 less than 2, right? Hence the determinant is 0. But we have manually calculated here. You can even argue like this. Okay. Okay. Next, next we'll go to the finding the formula of the writing the formula. You won't find the formula as such. We'll write down the formula for n cross n matrices. Not n cross n. We'll go to the third case, that is 3 cross 3 matrix. Okay. So let us take a 3 cross 3 matrix. I'll write the numbers like this: A11, A12, A13. Okay, what does this notation mean? If I have Aij, it means that the element lies in the ith row and jth column. Okay, so A11 means first row, first column. A12 means first row, second column. A13 means first row, third column. Okay, so A21 second row, first column, second row, second column, second row, third column, third row, first column, third row, second column, third row, third column. Okay, this is the thing. Now the formula for calculating this is, there are many formulas, but I'll teach you only one. There's less time to teach all the other ones. Okay, so this is the basic one I'll teach all. So what you're supposed to do is you calculate A11 multiplied by determinant of A22, A23, A32, A33. Okay, so and here you write minus 1 to the power 1 plus 1. Okay, we are writing determinant of A over here. A is equal to this matrix. Determinant of A will be this numbers. Yeah, so what have I done here? I'll just explain. I have written A11, that was this element here. Where is it? Yeah, it was this element here, right? So this element I have written here in the down below, and then I delete this column and I delete this row from this matrix. What remains is only this 4 elements, right? If you delete this row and this column, what remains is only this 4 elements over here, right? So I'm finding the determinant of those 4 elements because I know how to find a determinant of a 2 by 2 matrix. Okay, so here I find a 2 by 2 sub matrix of this. It's like a subset of the original matrix, so that I'm writing. Next, what I've done is I had multiplied a minus 1 to the power 1 plus 1. From where did that plus 1 come? The plus 1 came from this. So basically I'm adding up both the subscripts over here. Okay. So now it's not done with the formula. Next I do the same thing. I write plus times minus 1 to the power. I'll write this a1 2. So this should become 1 plus 2 a1 2, and then what you do is you have to find the determinant of a 2 by 2 matrix. So we will find a 2 by 2 matrix. This is called as a pivotal element for this case. Pivotal means the leading element, as such you can think of the element which leads the process. So here you have a12, right? So I wrote a12 over there. Delete this column and delete this row from the matrix. In your mind only do that. So delete this row from the matrix and delete this column from the matrix. What will remain? Write down the entries which remain. A21, A23, A31, A32. Done. Next, I'll write the next element over here. Plus minus 1 to the power. The next element is A13 over here. Okay, so A13. So repeat the process. A13. What I had done is I started with this, then I went to this, and then I've gone to this now. Final element. So delete every element which is in this row and this column. What remains here is this. A21, A31, A22, A32. Okay, this 4 elements over here will become a part of this thing. This 4 element, this 1, 2, 3, 4. Okay, so this 4 elements will become a part of the determinant. How did I get them? Delete this row, delete this column. Delete this row and delete this column. What remains are only these 4 elements. Come, let us simplify this now. Minus 1 to the power 1 plus 1. So this is minus 1 the whole square. This will become minus 1 the whole square will become plus 1. Okay, minus 1 the whole square is plus 1. So A11. This determinant I'll calculate. I know how to find 2 by 2 determinant. So this will become A22 into A33 minus A32 A23. Okay, and then this will become, next is minus 1 to the power 1 plus 2, that is 3, right? So this will leave me with minus 1 to the power 3, that is a negative minus 1. A12. Okay, then you multiply with this A21, A32, A31, A23. Next is going to be minus 1 to the power 1 plus 3. A13, the plus sign now. So will become A21 into A32 minus A31 A22. Okay, so this entire giant thing what I have written down here is a formula for the determinant of 3 by 3 matrices. Okay, so this is the big and simplified formula. There can be more versions of this, but this is just like the simplest one. So I've given you all. Right, there are other ways of calculating the determinant. That is, this method is called as expanding along the first row. Expanding along first row. Expanding along first row. Okay, expanding along first row. This is the name of this method over here. You can expand along the first column, second row, third row, and also on third column, second column, and so on. Okay, so I have done only this one because this one has a small pattern in it. Okay, there are other things you can expand on second row, third row, and all. But that requires a little bit of patience and work. Okay, sometimes that might be easy, this might be difficult, but whatever. Okay, so let us continue. So let us solve some examples. Examples. So we'll see the example as A. Okay, give me some numbers. 1, 2, 3, 4, 5, 6, 1, 1, 1. Okay, so let us calculate according to the above formula. Determinant of A, this will be equal to, write the first element. Okay, first row, first element, then 5, 6, 1, 1, determinant of this people, minus the second one. Just remember the formula above. Okay, the first one is plus, second one is negative, third one is positive. Okay, so 2, 4, 1, 6, 1. Okay, delete the row which contains this 2 and delete the column which contains the 2. So what remains is 4, 1, 6, 1. Okay, next is going to be positive. This number is 3 over here. Okay, and then delete the row and column which contains 3. So first row is gone, third column is gone. What remains is 4, 1, 5, 1. 4, 1, 5, 1. No, sorry, my bad. 4, 1, 5, 1. Okay, so 5 into 1 minus, this is 1 into 5 into 1 minus 6 into 1, 2 times 4 into 1 minus 6 into 1, so 4 minus 6. So 4 into 1, 6 minus 6 into 1, this is going to become 3 times 4 into 1, 5 minus 5 into 1, so 4 minus 5. Okay, so let us write down these numbers. This is going to become minus 1. I'm just using square brackets, and this does not mean it's a matrix over here. Sorry, I should have thought about this. I'm just using ordinary square brackets to show these things. Next time I'll use curly brackets, round brackets. So this is going to become 2 into minus 2. It's better to write it like this instead of square brackets. This is going to become 3 into minus 1. Minus 1 plus 4. Minus 1 minus 1 plus 4 plus 4 minus 3. Minus 1 minus plus 4 minus 3, and this is going to become 0. Okay, so as I told you previously, the rank of this matrix is actually less than 3. Okay, that's why this thing has become 0. Yeah, you can easily see that it is going to be so, because if you subtract the first row from the second row from the first one, sorry, from the second row subtract the first row, what will happen? You'll get 3 3 3 over there, and your third row is 1 1 1. So use this 1 1 1 and kill this fellow, so you'll get all 0 0 0 over there. So that's why the rank of this matrix is going to be less than 3. Okay, because you're going to get one full 0 row in it. Okay. Okay, so moving on. Take some other numbers now. Second example, we're going to take this as a is equal to 1 3 2 2 1 3 3 2 1. Okay, so this matrix, so let us calculate determinant of A. This is going to become 1 times, delete this row which column which contains 1 and row which contains 1, which will leave us with 1 3 2 1. Okay, next element comes with a minus sign, minus 3 times 2 into 1 3 into 3, so 2 1 3 3. Okay, so next will be plus 2, this will become 2 1 3 2, 2 1 3 2. So this is going to become 1 minus 6, use this curved brackets, minus 2 minus 9, sorry, plus 2 times 4 minus 3, 2 into 2 4 minus 3. This will become minus 5. This will become 3 into minus 7. This will become 2 into 2 into plus 1, not minus 1. Okay, so this will become minus 5 plus 21 plus 2. This will leave you with 14. is the answer. Sorry, not 14, 16. Check again. 2 plus 23, 23 minus 5. Yeah, 16, 18. Okay, this will become 18. One more we'll try. Example number 3. So in this case, my matrix A is given as no, we won't take 0 there. We'll take 3, 0. Okay, 3, 6 will take 3, 6, 1, 2, 1, 3, 3, 4. Okay, and this is 0, this is 0. On this I'll take it as 0 then. Okay, this I've taken as 6. This is 6 and this is 0. Okay, so let us try to calculate the determinant of this matrix. $37 0. Okay, so this determinant of A over here will become so 3 into this thing will be 2104. Okay, minus 6, we'll get 0 0 1 4. Okay, last one is going to become plus 1 times 0 0 2 0. Okay, so in this case 3 into 8 into 8 minus 0 minus 6. Here you'll get 0 minus 0, so it will be 0. Here you'll be getting 1 into 0 into 0, so that will be 0. Okay, so this leaves you with 24. Okay, now observe what has happened here is the contribution of this second and third term is 0 over here, right? So what is this determinant we have obtained here? The determinant is nothing but actually 3 into 3 into 2 into 4. Okay, 3 into 2 into 4, which is 24 for you. Okay, so that's what we observe from this, that the determinant is nothing but the diagonal elements, so product of the diagonal elements. Okay, so this is the thing. Okay, so now having done so many examples, let us see some properties of this. Okay, so let us see some properties of the determinant. And before I go to properties now, let me just tell you the special case which you have done above basically. Special case. A matrix of the form, matrix of the form form where where it's of the form where the entries outside the diagonal, rather the entries outside the diagonal are 0. By the way, this should be an n cross n matrix. N cross n matrix of the form where the entries outside the diagonal are 0. That is Aij is equal to 0 when I is not equal to j. Okay, is called a diagonal matrix. Called or diagonal matrix. Diagonal entries are what, by the way? Diagonal entries are aii. Okay, so this is basically the elements which lie on the diagonal of a matrix. So if you have a 2 by 2 case, the diagonal is this 1 1 and this is 2 2, right, and the entries outside that are 0. Okay, then next is for 3 by 3 case, you'll have a 3 4 7 0 0 0 0 0 0, right. This is called as a diagonal matrix of order 3 by 3. Same way you can go for 4 by 4, 4 3 3 2, here is 0 0 0 0 0 0 0 0 0 0 0 0 0. Okay, so these are called as diagonal this thing matrices. Okay, again this entries are on the diagonal of the matrix. Okay, so this is on the diagonal of the matrix. See, when you have a square, you have a diagonal of a square, right? So basically that's what is happening here. These entries are actually lying on the diagonal of the square over there. Okay, so that's why they're called diagonal entries. Yeah, and what are the subscripts of this entries? In this case it is a11, a12, sorry, a22, and here it is this is a11, this is a22, this is a23, sorry, a33, and this will be a44 by that same logic. So diagonal entries have the subscript as II, and the elements which are not on the diagonal, the subscripts are ij, but I and j are not equal. Okay, and all those entries have to be 0. By the way, on the diagonal also, this is also a diagonal matrix. 1 0 0 0 0 0 0 0. Okay, yeah, this is also a diagonal matrix, even though two of the diagonal entries are actually 0. Okay, these two entries over here are 0, but still it is a diagonal matrix, because what is the condition I have said here is that the entries which are outside the diagonal should be 0. On the diagonal, all of them can be 0 also, I don't mind. Okay, but outside who are there, they should compulsorily be 0. Okay. Yeah, so moving on. Special, yeah. So now, since we have defined this, the property which we have is property diagonal, sorry, determinant determinant of a diagonal of a diagonal diagonal matrix is the product of its diagonal entries of its diagonal is the product of its diagonal entries. Determinant of a diagonal matrix is the product of the diagonal entries. Okay, so just going upward, this is a property. I won't prove this property here. And by the way, what is there to prove also? You can easily see the proof is correct. Okay, just notice this. It's very obvious. The proof is also very obvious. Why it is true? You take any 3 by 3. If it's true for 3 by 3, you can easily say it's true for this thing. So you have A11, A12, sorry, A22 and A33. 0, 0, 0, 0, 0, 0. If you try to calculate this one's determinant, what you'll get? You'll get A11 into A22 into A33 minus 0, and rest everything is going to be 0. Right? So what remains here is A11 into A22 into A33. Right? So this is the proof for 3 by 3 case. For 2 by 2 case, it's much easier. If you have A11, A12, sorry, A22, 0, 0, find the determinant here. What is it? 1, 1 into 2, 2. Okay. So it will be true for 4 by 4 also. Okay. So yeah, I am not taught you how to find determinants of 4 by 4, but you can extend the method what I did for 3 by 3 to 4 by 4 also. Okay, but we won't be going there right now. Yeah, so what is the determinant of this matrix? Determinant of the first matrix over here, this one's determinant of this matrix here is 2. This is determinant is 3 into 4 into 7. How much will that be? That is 12 into 7. So 70 plus 14 is 84. This answer is 84. This is 4 into 5 into 3 into 2. This one's determinant will be 4 into 5 into 3 into 2. So this will become 5 4s are 20 into 6. This is going to be 120. Okay. And this is going to be what? 1 into 0 into 0. So determinant is 0. So I told you if determinant is 0, rank has to be less than n. And you can clearly see in this case, the rank of this matrix over here is 1. It has only one non-zero row in it. Right? And there were 3 rows actually, but you have only one non-zero row. So rank is less than 3 and hence determinant is 0. Okay. Okay. Next. Next special case, write 1 over here. This is case 1, you can see. Call this case 1 where we define the diagonal matrix. Okay, next we will go for the okay. So here we are. So now you get your A. Case 2 we are doing. Right, case 2 first. Okay. N cross N matrix whose whose all entries below the diagonal n cross n matrix whose all entries below the diagonal are 0 is called as a low upper triangular matrix. It's called as n upper triangular matrix. Okay, so let's underline here upper triangular matrix. Okay, example, the notation basically is going to be of this form, like A11, A22, A21, 0. This is in the 2 by 2 case. 3 by 3 is A11, A22, A33, A. Okay, so this is how the upper triangular matrices look like. Okay, so same way you can also define a n cross n matrix whose all entries the diagonal above the diagonal are 0. Above the diagonal are 0 is called a whose all entries above the diagonal are 0 is called as a called as a lower triangular matrix, because the entries below the triangle diagonal are 0, non-zero. That's why it's called lower triangular. The side which has non-zero entries, that side's name it gets. If it has upper side, it has non-zero entries, then it will be called as upper triangular. Lower side, if it has, then it will be called as a lower triangular. Okay. Okay. Above the diagonal are 0 is called as a lower triangular Okay, so basically it's of the form, in 2 by 2 case it will be A11, A22 and A21, and here there is a 0. In 3 by 3 case it is like this, A11, A22, A33, A23, A sorry, this is A32, A32, A31, A21, 0, 0, 0, 0. Okay, so this is the case. Okay, So this is how lower triangular matrices look like, and this is how upper triangular matrices look like. Why the name triangle? Yeah, it's a little clear from the design of this. Just observe this design. It forms like a triangle over here. Okay, same thing over here. This is also a triangle, right? Can you see there's a triangle formed there? So this is upper triangle because the triangle is on the upper side. Here you have a triangle on the lower side. So that's why you get a lower triangular matrix. Above the diagonal are 0, below the diagonal may or may not be 0. Okay, so that's why. Okay, so let us see some examples. Before I give examples, a matrix is said to be triangular triangular said to be triangular if and only if it is either upper triangular if and only if it's either upper triangular okay, if it is upper triangular or lower triangular. Okay, so now, so triangular means it's either upper triangular or lower triangular. There is a triangle inside the matrix basically. Okay, so now the property which we wanted to do, the determinant of a n cross n triangular matrix is the product of its diagonal entries. Okay, you take the product of its diagonal entries, you get the determinant of a triangular matrix. I have solved examples on this above. If you'll go and check some of the examples we have done earlier for 3 by 3 and 2 by 2 case, one of those matrices was actually triangular, and observe that this property is true. Multiply the diagonal elements and see that the answer is same. Let me only go and check it actually. Okay, just a moment. Okay, so let us see that. See, this was an example of a triangular matrix. The product of the diagonal elements is what? 3 into 2, that will be 6, and which is actually the answer which you got here. Okay, only one was there over there. Where is the other case? Just one moment. I see the example is. Yeah, so see this example over here. The here also you had a diagonal, here you had a upper triangular matrix. The diagonal is 3, 2, 4. Diagonal elements are 3, 2, 4. The product is going to become 3 into 2, 6. 6 into 4 is 24. And that's same as the determinant which we actually found here. Okay. So, yeah. So, we were writing this down. Let me zoom out and go there. Yeah, here we were. Okay, determinant of an n cross n is product of its diagonal entries. Okay, if you'll calculate the determinant, actually this property is true. Yeah, one more thing to note, which might be confusing for some of you all, but the thing is that note a diagonal matrix, a diagonal matrix is both an upper triangular matrix, an upper triangular triangular matrix, and a lower triangular matrix. It's upper triangular also and lower triangular matrix also. Okay. Why is that so? Just see how our diagonal matrix looks like. 1, 2, 3. Here you have 0, 0, 0, 0, 0. Right? So see, what is an upper triangular matrix? An upper triangular matrix is the entries below the diagonal should be 0. Okay, so are they 0 in this case? Below the diagonal? Yes, they are 0. So this becomes an upper triangular matrix. I never put any condition on what kind of elements you write above the diagonal. Okay, I only said the elements below the diagonal should be 0. So that's happening now. So it's an upper triangular matrix. What happens above the diagonal, I'm not worried about it. Okay, next observe that the entries which are above the diagonal, they are also 0. Okay, so the entries above the diagonal are 0. What happens below the diagonal, I'm not worried about. Okay, so hence this matrix is a lower triangular matrix. Yeah, by that logic, this matrix which is completely full of zeros, this matrix is everything. By the way, this is triangular, this is diagonal, okay, everything it's triangular, it's diagonal, it's the many other things about it, but not go into those things right now. Okay. So next we'll go to some properties of this matrices. So properties of determinant, properties. Okay, first property, if any it's not only row, it's also for a column. If any row or a column of a matrix are 0, then then determinant of A is equal to 0. Okay, if any row or column of a matrix are 0, then determinant of A is 0. If any row or column of matrix is 0, then the determinant is 0. Okay, proof I won't go into, but it's not so difficult. Next, second property. Uh, if any two rows if any two rows are identical, okay, if any two rows are identical of the matrix are identical basically, or identical or are scalar multiples of each other, then if any two rows are identical or scalar multiples of each other, then determinant is again 0. Why is this so? Let me just tell you the proof in brief. Why is this so? If your two rows are identical, what you can do? You can use one row and make the other row 0. Okay, so the moment one of your rows becomes 0, that means your rank is less than n. If your rank is less than n, I told you earlier on that the determinant has to be 0. Okay, same way, even for the first one, if you have one entire row or a column which is identically equal to 0, then what will happen here is, if you have one entry row which is full of zeros, again your rank is less than n and hence determinant has to be 0. Okay, what I'm saying for rows is also true for columns. So you can write columns here in bracket. You need to columns. Okay, okay, so these are two properties which will help us in calculating the determinants faster. Okay, the moment you see some zeros or somebody is a scalar multiples of each other, then it is going to be true. We had done a similar problem sometime back. We had seen this example. Remember this example which we saw earlier on in today's class at the beginning when we were talking of 2 by 2 matrices. The second row is actually 3 times the first row. Okay, and this will lead to yeah, this if you try to calculate, yeah, if you can actually do row elimination, and you can calculate this is 2300. Okay, once you perform that row operation, and now you know you have a 0 row here, and hence this is going to give you determinant of A is equal to 0. Okay, same thing can be thought about for 3 by 3 matrices also. Okay, okay, so moving on, the third property. The third property, 1 2 3, if the jth row this condition is true for column also, so I'll just write column in bracket. If the jth row can be expressed can be expressed as Rj is equal to some k times Ri plus jkl. Yeah, so just a moment. K times Ri jk. Which alphabet I'll use now? A J K L M N O P Q. P is there. So P times some wait, R I J K. I used K also. Set R L. Okay, R L. So basically, what I'm doing is I'm writing this row as a combination of two more rows, right? So then determinant of A will be also 0. Why is that so? Because if I perform the operations, see what are the operations I'll have to perform? I'll have to perform R, J. From that I subtract K times minus K times. I subtract K times the ith row. What will happen? This term is going to disappear, right? Performing this, and what is the other operation I should perform? From the jth row subtract the lth row minus p times. Okay, yeah, so jth row subtract p times or add minus p times the lth row, right? So this term will also cancel. Okay, by performing these two operations we get a zero row, okay, hence determinant will be 0. Okay, hence determinant of this will be 0. Yeah, so let me show you one example on this last one. So take A to be equal to this matrix. Okay, so 1 2 3 4 5 6, and the third row now I'll just keep as the sum of both of them. So 5 7 9. Okay, the third row is kept as a sum of both these rows. Okay, I'll calculate this determinant and show you that it's actually 0. Okay, so I know if I that if we perform the operations I can show that this thing has rank less than n, and then hence the determinant is 0, but I want to show it manually that it is 0. Okay, so determinant of, yeah, this is your matrix A. When you're writing matrix A you put a square bracket. When you're writing determinant just put the bars. Okay, so yeah, so let us calculate 1 into determinant of 5 6 7 9 minus 2 times determinant, it will be 4 5 6 9, and third thing will be 3 times 4 5 5 7. Okay, this will be 5 into 9, that will be 45, minus 7 6 are 42. Okay, minus 2 times 9 4s are 36, minus 30, and this will become 3 times 7 4s are 28, minus 24. Sorry, 25. Sorry. Okay, so this will leave you with 3. This leaves you with 2 into 6. And this leaves you with 3 into 3. Okay, so this is equal to 3 minus 12 plus 9. As you can see, this sum is 0. Okay, so hence this property is true. The other two properties, they were a bit clear, no? So I won't solve an example on them. Okay, yeah. Yeah, the second one also I'll show you with an example then. Okay, yeah, the second property example, just consider this A, 1 2 3, 1 2 3, and here you can put 4 5 6. Okay, two rows are identical over here. Two rows are identical, right? So let me verify this thing. So 1 into 2 3 5 6, minus 2 times 1 4 3 6. So this much. 3 3 into the determinant of 1 2 4 5. Okay, 2 into 6, this will give me 12, minus 5 into 3, that is 15. Okay, minus 2 times 6 minus 12. Okay, and this will leave me with 3 into 5 minus 8. Okay, so the first one contributes minus 3, second one contributes 2 into minus 6, and third one contributes 3 into minus 3. So this will add up as minus 3 plus 12 minus 9. Again 0, but for some weird reason it had the same numbers as the previous one, 3 12 and 9. Coincidence. Okay, so this is one example that if you keep two rows equal, you'll get a 0. The first property was very obvious. If you keep all rows 0, then you get, if you keep all entries of one row 0, then you get a determinant as 0. Anyways, for exams, if I give you all such kind of problems, no, you can directly write the answer that this determinant will be 0 because the first row and second row are equal, or that other case the determinant was 0 where the third row was the sum of the first two rows, and so on, right? So if you'll find this particular information during exams when you're solving the problem, if you realize that two rows are identical, or one row is the sum of two more rows, or that one row is sum of two more rows, or what else is there? Yeah, all entries in two rows are equal, right? So in this three cases, you can directly write down that determinant is 0 without doing any calculations and all. Okay, look at the question, write down the answer. Okay, no need to do all these calculations. And for exams, I'll usually ask that kind of questions only where the answer is directly known as 0. Okay, so that you all can save your time without solving the problem. You should be able to get the answer kind of. Okay, but yeah, if you'll start solving the problem and then you'll get stuck while doing it, or you'll made a mistake or something, then I don't know. Okay, so better try to keep these properties in mind so that you can solve the problems using the properties only without having to go to the uh, actual calculation. Okay, so this was about determinants and some of the properties. Okay, so let us continue forward to some more properties. Property number 4. Okay, so the thing is, if you interchange any two rows of a matrix, interchange any two rows of a matrix, then interchange any two rows of a matrix, then the sign of the determinant changes. Determinant changes. Okay, so basically, if it was plus before, it will come minus. If it was minus, it will come plus. Okay, let us see this with an example. So I'm purposely doing 3 by 3 examples earlier so that I'll get practice in solving this. So A is this matrix 2, 3, 4, 5, 6, 7, 7, 9, 8. Okay, so this is a matrix. If I interchange this, yeah, we'll have to calculate this determinant first. This one's determinant will be determinant of A is going to become 2 into 6 into 8 minus 7 into 7. Okay, minus 5 minus 5, this will become 8, 3 into 8 minus 4 into 7. Okay, I have not written that one step in between. Let's try to do this a bit fast. Okay, so 4 into 7. Okay, next is going to become plus 9 times 3 into 7 minus 6 into 4. In case some of you found this confusing, then please write down that missing step which I have not written. Okay, yeah, so this will become 2 into 6 into 8, 8 6 are 48, 7 into 7 is 49, 7, 49, 6, yeah, it's correct. So 8 3s are 24, 7 4s are 28, plus 9 7 21, and this will become 24. So this will become 2 into minus 5 . 4, 8. Yeah, 4 into 8 minus 49. Yeah, this minus 1, not 5. Minus 5 was here. So 24 minus this thing. This will leave you with minus 4, and this will become plus 9 into minus 3. Okay, so this answer will become, this will become minus 2 plus 20 plus minus 27. So minus this thing, all this will leave you with minus 9 as your answer. Answer is minus 9 of this determinant, value of this determinant. Now what I'll do, I'll do the same thing, but I'll interchange the rows of the matrix. Okay, you can do this by interchanging the columns also, but I'll focus more on rows. Okay, so perform, write this below. I'm writing sideways, don't mean you write sideways. Okay, so performing, I'll interchange the second and third row. So R2, 3, any two rows you can interchange. I'll interchange the second and third. So performing R2, 3, we get A is equal to, it's a new matrix, so we'll call it as A dash. So 2, no, don't call it A dash, A dash is something else. So what we'll call it as, we'll call it as A tilde. Okay, basically tilde is this symbol. Okay, so it's like a curved hat or something. Think of it like that. Okay, so first row as it is 259. This is 478, 367. Okay. So let us calculate determinant of A over here. This will become 2 7 into 6 into 8. Okay. Okay, so continuing, this will become next minus 5 into 4 into 7 minus 3 into 8. Okay, 4 into 7 minus 3 into 8. Next will become plus 9 times uh, 4 into 7, sorry, 4 into 6 this time. 4 into 6 minus 3 into 7. Okay, so this will leave me with 2 into 49 minus 48 minus 5 times 28 minus 24. This will leave you with 9 times 24 minus 21. So this will become 2 into plus 1 minus 5 into minus 4. Okay, this will leave you with 9 into 9 into 3, and this is plus 4 or minus 4. 9 into 3. Okay, so this is going to be 2 minus 20 plus 9, sorry, plus 27. Plus 27. Okay, so you have what you will get in the end is plus 9. Okay, it's going to become 29 minus 20, which is going to be plus 9. So what I did, I interchanged one row over here and I got the answer is minus of this determinant. The sign changed. It was minus before, it became plus now. You can continue this operation. You can interchange some other two rows from this matrix. The answer will again change with a minus sign. Okay. If we interchange any other two rows other than 2 and 3. Okay. So interchange 1 and 3, and for homework you can check the answer will become plus 9. Sorry, minus 9 it will become because you're interchanging one more time. No. Okay. So let me just write the thing here for homework. For homework, I want you all to show me that I'm interchanging the first and third row. So 4, 7, 8, I'll keep as it is. 3, 6, 7, 2, 5, 9. Show that this answer will become minus 9. Okay, show that this determinant over here will become minus 9. Okay, so that being done, let us go further to the next property. It's the mouse. Okay, let's. Where's the mouse gone? Here it is. Okay, so this is the property which said that interchanging any two rows of a matrix will then the sign of the determinant changes. Okay, same thing holds true for columns also. Just write in bracket, it's true for columns also. Any two columns, but don't interchange a row and a column. That can't be done. So rows you interchange with rows, columns with columns. So then also this property holds true that the determinant will change only in sign. Okay. So moving on, next property. Okay, the fifth property. If the matrix A is of the form A11, A12, A13, okay, then A21 plus some element D, A22 plus D, A23 plus D, and A31, A32, A33. Okay, means there is a common term which is added to all three elements over here. Then determinant of A can be computed like this. You can write A11, A12, A13. Then you can write A21, A22 and A23, A31, A32, A33. Okay, plus this. So basically the determinant splits into two sums, A12, A13, D, 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 A31, A32, A33. Okay, you can split it into two different determinants. Okay, so let us see one example based on this. Example, example, take A to be the matrix 1, 2, 3, 4, 4, 5, 6. Okay, 4, 5, 6. And then you have your data. So look on 6, 5, 6, 5, 6, 6. Okay, assume this is the matrix given to you all. Then you all can see that this matrix can be split like this: 1, 2, 3, 1 plus 3, 2 plus 3, and 3 plus 3, 6, 5, 6. So this can be written as 1, 2, 3, 1, 1, 2, 3. Yeah, so 1, 2, 3, 6, 5, 6 plus, yeah, this is determinant of A can be written like this, huh? Not the actual matrix, huh? Actual matrix, if you write like this as a sum, it becomes something else really. So ensure that you're writing the determinant symbol at this stage, huh? Yeah, so this will become 1, 2, 3, 3, 3, 3, and 6, 5, 6. Okay, this can be written like this. Yeah, so now this determinants are a little easier to calculate compared to the previous one. This determinant becomes 0. Why? Because two rows are same, right? Now only this determinant we have to calculate. So that will become 1. Right, this side and this side, this side. This determinant is 0 because two rows are exactly same. Next, this will become 1 into 3 into 6 minus 5 into 3 minus 2 into 3 into 6 minus 3 into 6 plus minus 6 into 3. Okay, last term is going to become 3 times 3 into 5 minus 6 into 3. So this is going to come 1 into 18 minus 15. This is going to become 0 because 3 into 6 minus 6 into 3 it is. So this will become 3, 5 3s are 15 minus 18. 18 minus 15 is minus 3 plus 3 times 15 minus 18 will give you another minus 3. This will leave you with minus 3 minus 9 is equal to minus 12. This is your final answer. Okay. So this is a kind of an easier calculation than the original matrix, because notice that this calculation involved only 3's over here. Okay, only 3's are getting multiplied into something. That is a much easier thing to do, right? But yeah, this property is obviously difficult to use because you cannot predict it easily how you'll, what will be this term d which you have to add to each number. Okay, it's not easy to think of this because this 4 can be written as 1 plus 4. You can write this as 1 plus 5. Sorry, 1 plus 4. You can write this as 0 plus 4, 1 plus 4, and 2 plus 4 also. That can also be done. Okay, you can write it also as 3 plus 1, 4 plus 1, 5 plus 1. There are many ways of doing this thing. Okay, I purposely selected it this way so that I can make the first one, second row identical and hence get the answer as 0. Okay, not always this will be easy and obvious. So this property is very rarely used like that. Okay, so this is the end of this property also. Okay, so with this we have finished almost everything what we had to do with determinants. Okay, so we've covered a lot about this determinants. I have done everything for only 2 by 2 and 3 by 3 case. I have not discussed anything about 4 by 4 case, but let me just briefly explain to you what will be happening in 4 by 4 case if you had a 4 by 4 matrix. Okay, so I'll just briefly explain this thing, and the same logic can be applied for 5 by 5 also. So if you have a 4 by 4 matrix here, A11, A12, A12, A13, A14, right, A21, A22, A23, 23, A2, A12, A23, A24, A31, A32, A33, A34. Always keep in mind, for getting a determinant you require square matrix. Number of rows and columns should be same. A3, sorry, A41, A42, A4, A44, okay. So this becomes the A is this, then determinant of A is will be minus 1 to the power A11, A11, so the power over here will be 1 plus 1, okay, into determinant which you get of the matrix, submatrix, which you get by deleting this, see, delete this column and delete this row. Okay, delete this row and delete this column. What remains, we'll get it as a determinant of this matrix. Okay, so A22, A23, A24, A33, A34, A42, A4 and 3, and A4 and 4. Okay, next it will become minus, right, plus into minus 1 times 1 plus 2, A12, this entry, okay, into determinant of delete. See, what you have to do is delete A12 is here, no? So delete this row and delete this column. Now whatever remains, take the determinant of that. So A21, A2, A31, A41, A4, A4, A33, A34, A3, sorry, A23, A23, A24. Okay, are we done? No, we have to write for the others also. 1, 3 and 1, 4. Okay, so plus minus 1 to the power 1 plus 3, A1 3. So delete the first row and third column. So what remains is 2 1, A2 2, A2 4, A3 1, A3 2, A3 3. Sorry, A3 4 this will be. Then A4 1, A4 2, A4 4. Okay. So next is minus 1 to the power 1 plus 4. A1 4. Okay. This will become, delete the first row and the fourth column. So A2 1, A2 2, A2 3, A3 1, A3 2, A3 3, A4 1, and okay. So this is what we get. Okay, so this is the determinant of a 4 by 4 matrix. Now only thing you have to simplify this powers over here. Okay, I know I told you how to calculate a 3 by 3 determinant in the previous part, right? So that I won't elaborate more. What I'll write down here is only this simplifications. This is the modulus of the determinant of A is minus 1 to the power 1 plus 1. 1 plus 1 is 2. Minus 1 to the power 2 is plus 1. So this will become A11 into that determinant which I have told you to calculate out there. And this will become 1 plus 3. So that's 3 and 1, minus 1 to the power 3. So minus 1 cube is what? Minus 1 into minus 1 into minus 1. So that will become plus 1 into minus 1, which will leave you with another minus. It will leave you with minus 1. A12 A12 into the determinant above. Then here you have 1 plus 3. So that will give you it as a plus 4. So minus 1 to the power 4, that will leave you with A13 over here into that determinant to be calculated. Okay, I'm not writing those entries on, there's no place this way. I'll write this term again, and then minus 1 to the power 1 plus 4. 1 plus 4 is 5. So minus 1 to the power 5 will leave you with a minus 1. So minus 1 into A14 141. Okay, so this is the things you all have to only calculate this 3 by 3 determinants which are a part of this process. Okay, so with that we'll stop for today. Okay, so this is a quite lengthy video. I have covered everything about determinants. In the next class we'll learn how to use determinants to find the inverse. Okay, so that's all for today. Thank you for watching. Bye bye. Bye bye. Bye.